Okay, so let's start. I'm Nobuo Kawaguchi, and today I talk about the state of the art of indoor localization technology. So a little bit specific topic, but maybe some of you have some interest on this. Okay, so let's go. So today, starting, these are my topics about today. So what is location? And I talk about okay, so there's a lot of standards around the location. So I explain about that, and also overview of indoor localization technology, and more specific about things about the localization technologies, beacons, IMES, Wi-Fi based pedestrian dead reckoning, and magnetic field, and hybrid technology. And finally, I talk about a little bit about the indoor maps. Okay, so what is location? So of course you know about location or position. So it's very familiar, and also every object in the real world has a location somewhere. And we can say it's a geographical point, and maybe it's not only a point, but maybe area. And we can say absolute location, like axis, x-axis, y-axis, something, and also relative axis, so close to me, or west, south, north, south, like that. And when we try to figure out which location it is, so we require some map or satellite image or aerial images or illustration map. So it's not accurate coordinate, but we usually use this kind of different kind of maps using for pointing the location. And there's a lot of various standards for location. So ISO 6709, you know about the latitude, longitude. It's defined at here. And also there is another extra field called CRS. I'll explain that. And there are different location standards like POIX. POIX means a point of interest exchange language, and a GXML and a GML, and also place identifier. And for CRS, it's called Coordinate Reference System. Have you ever heard about CRS? Maybe Sui-sensei know about that. There are a lot of coordinate reference systems, and okay, so Japan has currently we think we should know about the 3 different kind of coordinate system. Tokyo coordinate reference system. It was used until 2002, and the JGD 2000 was used until 2011. And now we are using JGD 2011 because the big earthquake in the east side of Japan, the Japan's coordinate a little bit differs, so we have to change it. So that's the reason why we changed the coordinate reference system in this year. And you know about the GPS, and GPS is based on WGS 84, okay? And it's different, but very closely related. So maybe the difference of them is just a few centimeter or few millimeter, but JGD 2000 with Tokyo, there's a big difference. It has maybe 400 meter or 500 meter difference. So if you have a map, an old map, and so it may be based on Tokyo CLS. So you have to be curious about which coordinate difference system they're using. Okay. Okay. And also I'll explain about EPSG. So there's a lot of coordinate reference system in the world. Okay. Sorry. Okay. So as I show you, okay, Japan has 3 at least, but also we have different. This is a coordinate reference system for mapping for the geoid. So it's mapping on the Earth. So it's using the ellipses. However, in a usual area, we should use optional coordinate system. So that is completely different, but it depends on the place. So we have 19 systems in Japan. So different coordinate system in the 19 area of Japan. I'm sorry, I don't show you, but only in Japan we have 90s for each. Okay, so lot of coordinate systems for the precise location. So to think about such kind of the coordinate reference system, so we need some kind of the standards for expressing them. So EPSG, European Petroleum Survey Group, they were, how to say, try to find out the petroleum in the world. So they need to some kind of the standard coordinate reference system. So they define EPSG, European Petroleum Survey, EPSG reference, and they have a registry here. Okay, I'm sorry, I didn't show. Oops, I just forget to put it. Anyway, okay. So so you can check from here about CRS. So if you put, for example, this number, EPSG 4326, so it means WGS48, and you can see the explanation about WGS48 at here. And if you can search from the keywords, so you can search JGD 2011, so you can find out what kind of coordinate it is using. Okay, and from here, I just find last night it has 16,000 CRSs in the world. So different kind of the coordinates in the world for describing the location. Okay. And there's also a standards group in the ISO, International Standardization Organization, TC211, 211. And 211 is a working group to develop standards for coordinates or geographical locations. And okay, they also provide a lot of ISO standards here. I'm not sure if the link works. No, I'm sorry. Okay, so anyway, so there's just a few places of them, and you can see these. Each box means some standards, and they are related. So a lot of standards related to the location work exists. So if you have to think about the location, so you have to know about these kind of the standards. Okay, so let's go to the localization technologies. Okay, so but for the outdoors, using the GNSS, it's a satellite system, a global satellite system, and it's easy to get the location using the GPS or GLONASS or other kind of the satellites. However, if you are indoor, you can't get the GPS signals, so satellite signals, so it is not easy to localize yourself. So we have to use the different kind of media, like radio frequency or magnetic field or light, audio, or other mediums. So by using such kind of media, to localize ourselves, we use following technologies called proximity or triangulation or scene analysis. So let's think about them. So proximity, so there's a several kind of reference point. Maybe it was a radio antenna, or maybe source of the audio signal, or maybe source of the emitting light or other medium. So if you get such kind of the medium information, so you can estimate you are close to such kind of reference point. Okay. However, it depends on the medium, but it's not easy to detect the distance between the reference point and your terminal. So maybe you just know about the you are close to that reference point. This is a close proximity method. Okay. And triangulation. So if you have several reference points, and if you have some way to measure the distance between the reference point with your place, so you can use lateralization. So using more than 3 reference points, you can calculate the distance, so you can estimate your location. Okay. Or maybe it's when you're using the radio frequency, you can use signal strength or maybe time of arrival. So how many how many microseconds or nanoseconds it required to how do you say, these signals comes to the emitting point, reference point, to your terminal. And there's another way called angulation. So you have two reference point, and if you can measure the angle to them, so you can also estimate your location. So maybe using the, how do you say, light communication, so you can estimate this kind of thing. Okay. And the final method or technology is called scene analysis. It's also called fingerprinting or footprinting. You know, fingerprint is differs on each person, and also signal pattern differs at different location. Okay. So for the scene analysis, you have to estimate your location using the different areas. So for example, this is some kind of the Wi-Fi signal, and maybe these rooms are, how do you say, shielded by the door. So here is the access point, and the signal comes to getting the weaker, but some point it get little bit getting powerful, and this in the room it's not well, but here you can still get the signal. So it depends on the how the buildings are formed. Okay. So to measure these kind of the signal pattern, you have to make an environmental survey by using the terminal. So the cost is very high. Okay, but you can get the high accuracy from that. Okay, so I will show you example about the indoor localization. There are several commercial products from the Docomo, Yamaha, and IMES, and Bluetooth low energy tags. And these are all proximity-based localization. And later I will explain about the more detail about Wi-Fi localization. Okay, so starting from the Docomo shop plat, these are services by the NTT Docomo. They show the users this kind of the smartphone application when you get into the some retail store, and if retail store has this kind of the audio beacon, sound beacon, and you can't hear the beacon sound itself, but it has a very high frequency signal, and it has an ID on the signal. So the smartphone can receive such signal by using microphone, so it can detect. And as far as I know, it have more than 1,000 shops built with this beacons. However, Docomo said, I just see their homepage. They will close the service in this July. So it seems it's not work well. Okay. And next example is Yamaha InfoSound. This is not a service, but it's just a library of technology. And this is a sound beacon. The beacon emits a signal, and Yamaha has a technology to put in some kind of the information on the sound. Okay? So that's the reason of the name, InfoSound. And by using this library, so you can make a stamp library. So if you get close to this beacon, so you can get some information, and the stamp is pushed to your smartphone application, or you can get a coupon from them. So these two, Docomo and Yamaha commercial product is based on the sound. Next one is IMES. IMES is an acronym of Indoor Messaging System. And IMES is using the same receiver of the GPS or GNSS. Okay? So now almost all smartphone has a GPS inside. So you can, but GPS, you have to receive the satellite signal. But IMES, this transmitter is just a small size, and they transmit the almost same signal from the GPS. Okay, so indoors, your smartphone can receive the signals from IMS, then you can detect your location. However, by using GPS, so you estimate your location by using the several GPS signals, maybe more than 4 satellite signals. Okay? But for IMS, indoor messaging system, it has a very weak power, so you can't receive several IMS messages. So you just get the one IMS. So IMS has just one ID. So IMS is also the proximity method. So it just knows that it's close to some IMS transmitter. And you have to know where the IMS transmitter is located. So you need some database of the IMS emitter locations. Okay. And there's other things. So Google have so each Android have a library inside about the indoor localization. So 2013, they provide new localization API, and it is based on proximity-based Wi-Fi localization. So even Android, if you you can't receive the GPS signal, still you can get the location, even in the underground or somewhere, maybe underground stations, because they use the Wi-Fi localization technology. Okay, but that detail is not clear. Okay, and also Google is also collecting the floor map called Google Floor Plan Services. So they try to get the floor plan data to gather the old world indoor maps. Also, Apple have another service called Apple Maps Connect. It's also for the indoor services. So for iPhones, also Apple collecting the indoor maps and also with Wi-Fi signals. They have an indoor survey app. So the shop owner or location owner have to survey their own location by using these applications. And in this Nagoya area, the Central Park in the Sakae area has enabled with this Apple Maps Connect. So if you can go there and you can use your iPhone, so you can check your iPhone is still working even in the underground shopping center. Okay, so why indoor is so important? So Google, Apple, or Docomo is trying to get something. So of course, most of the time, 80% of the time, we are indoor, and most of retail stores are indoor. So if you get a good recommendation or a good, services, so maybe you will buy some product. Okay, maybe you can get to navigate to some better store, a better restaurant or somewhere. So Apple bought the Wi-Fi Slam. Wi-Fi Slam is another Wi-Fi localization company to get their technology. And there's several venture company called Polestar or IN411. Okay, they are all indoor localization ventures, and they try to show you indoor maps and indoor navigations, and also indoor localization systems. So they are working ventures. Okay. Okay, so I will talk about more detail about the Wi-Fi scene analysis-based technology. So there's our paper, so I will explain more detail. And okay, so the steps of Wi-Fi localization, you have to model the Wi-Fi RF signals, and then you will localize by using the RF received Wi-Fi signal using the called particle filter. And finally, you will show the system will show you the estimated result. Okay. So for initially, you have to collect, make a survey of the Wi-Fi signal at the location of some place. This is an underground station. So we had as a survey like this, and we use the Gaussian mixture model to model this kind of Wi-Fi signal. Okay, so this is a concept of Gaussian mixture model. So there's several Gaussian distribution, and then it some of them, getting some of them, so we can get this kind of the little bit complicated line like this. Okay, but Wi-Fi signal is a little bit different from the Gaussian distribution, because Gaussian distribution, it's around here is round. However, Wi-Fi signal is very peaky at the point, of course. However, usually we require to estimate the location a little bit distant, have a distance from the antenna. So this area, if it fits okay about this area, so we think it might be okay. So we use to model by using the Gaussian mixture model about the Wi-Fi signals. So this is so IB building in Nagoya University, and we make a survey of each of points. Okay, then by this is just a point and strength, and then we model the all area of this area, this building like this. Okay, and so to make this model, it is not easy to convert this to here directly. So we start from converting this into the by the distribution or density of the points. Okay, so so this area, when it was strength is high, so density getting high, and strength is low, so density getting low. So how we convert them? So initially we had a measured point like this, and then divide the area by the Voronoi diagram, and then how do you say, make each area to distribute the point depends on the strength of the signal. Okay, so finally we get this kind of figure. Okay, so then by using the these point distribution or point density, so we can estimate the Gaussians. So from here, we have this kind of algorithm. So first we have to decide how many Gaussian we will use, and then make a clustering of them, and then using the EM algorithm to estimate most likely Gaussian mixture model from that. Okay, so for this one, we will get this kind of Gaussian. So different two-dimensional Gaussians put it. So now it has 7 Gaussian and then mixtured. So it can describe the power distribution of the from the antenna access point A, and this is just for only from access point A. So we will get the different signal from the different access points. So for only from A like this, and from different access point B like this, and from C like this. Okay, so we have a different kind of mountains from the different access point. Okay, then when we are in somewhere in this place, so we will get the different signal from the different access points. So we get some power from the access point A, access point B, access point from C. Then we have to estimate the location. However, so Gaussian mixture model, it is not easy to calculate the coordinate of some, how do you say, some power itself, okay? Some signal received strength. Okay, but the calculation cost is very important, so we use particle filter to do to make it faster. Okay, so I will show the demo. Okay, this is the iPad client demo. So initially we start from the survey phase. In the iPad we have a map of the building like this, and also we can just make a survey of this. So each pin shows the survey point. Okay, so when you put tap here, okay, so each point has a how do you say, the signal strength from the different access. You tap them, So you can get the Wi-Fi signal from different. So there's maybe 8 access points, and you can get the different signals from them. Okay. So from each access point, you can get the signal like this. So some access point like this, different access point like this. Okay. Can you see? And different access point like this. Okay. So then we will make the Gaussian mixture model for each this kind of the survey results. So we can get this from some access point and this from access point, different access point. So this is a modeling of the signal distribution in the inside of the building. So by using these models, so each red dot means a particle. And the particle is searching which is the best match point of the signal strength of the current received Wi-Fi with the model. Okay. So, so here he is in front of the door. So he is just placed like that, and the particle is searching the place, and then finally finds a location. Maybe this time the accuracy is around 2 or 3 meters. And when he moves, so particle is trying to find out the next point. Currently, it has no PDL system, so okay, it just moves like that. When he moves, and then the particle comes. Yes, yeah, he's. So now it's searching. The particle is searching the area. Okay, and then find out. But a little bit not close place, but maybe 5 meter difference. Okay. And okay, so this is the Wi-Fi. And also I will explain about the PDR. PDR is a pedestrian dead reckoning, the technology to estimate the location using the smartphone sensors. Okay. So it's tried to estimate how many steps and how far about the steps and the direction using the sensors in device, so accelerometer or gyro or pressure sensor. It is called SHS, and step and heading system. And it only measures the relative location. And when you'd like to get the absolute location, you require to integration with other localization method. And because it's a relative method, so when you use this, it will accumulate the error or noise. Okay. And in the literature, in the papers, we had a lot of papers already. So there are several issues. So a lot of PDRs are already in the commercial stage, and they have a different algorithm, different implementation, and different performance. However, so each commercial system do not show us any, evaluation value or something like that. So because there's no evaluation method, because PDR is so new. So also, accuracy depends on the distance and complexity of the what kind of route you walked. So, and also there are very limited evaluation data. We developed HASC IPSC, but it's only for 100 persons. So we had a PDR challenge the event called PDR challenge in the last year in the international conference called UbiComp. So it's trying to gather to evaluate the various PDL engine, and it's trying to evaluate the metrics for how to evaluate the PDL, and also we try to gather the data for evaluation to future PDLs. Okay, so we have to prepare several courses to evaluate, and then we asked to the participants to submit their own PDL algorithms, and then we developed an evaluation system, and the subjects walk to these courses, and then we get the result of the PDL algorithms. And then we evaluate all algorithms with all data from the subjects. So the PDL challenge is like this. So subject is walking like that, And we can calculate the location by using the radar sensors. Okay. And every movement is collected by the sensors inside of the smartphone as they are having. Okay. And the system, evaluation system like this. So each PDL, each smartphone, we have an algorithm inside. And then they send the data to the evaluation server. And also they put the PDL challenge corpus. Sensor data is put into the corpus. And then we evaluate the result to like this. And finally, we get 105 subjects, 343 traces, and a lot of data like this. And the result is like this. So you can see the blue line is assigned route. So on the upper side is, okay, so this area, upper area is overview of the floors. And this is the vertical view. So there is stairs, okay, like this. And some algorithms do not answer correctly. So these, each figure shows the different algorithms for same data. So for same data, different algorithms return the different results. So you can see this is not good. Little bit, how to say, not much like this. This is very good. This is also similar to this, and this is okay, also not good. But however, the vertical view is this one is good, and also this one is good. And finally, we got a lot of data evaluating them, and then get that this algorithm is very good. So the result is like this. So these are team name, and most best result is like this. So 3.5 meter error average is something. Okay. And in the final localization method, I will show you about the hybrid method. And to make hybrid method, we also add the magnetic field. Okay. Do you know there is a magnetic field around here? And also, usually we have a magnetic field from Earth. However, each building has its own magnetic field because the steel, big steel is inside. Okay. So there's a research to estimate the location of the robot like this. So we investigate this method into the pedestrian localization. So we measure the differences between the, how do you say, the time span. Okay, and then, okay, so in the September and January, so 4 months difference, a 5 month difference. And then it's also the IB buildings. And we can see there is a difference in the locations. So we can use these characteristics to estimate the location. And also, even in the 4 or 5 months, we have a similar result from them. So we think magnetic field can be used as a kind of landmark. Okay. And also, we model the magnetic field with the same Gaussian mixture model, which we used for the Wi-Fi. And we had this kind of algorithms to, how to say, estimate the location by using the different kind of sensors. And inside of them, we had the PDL algorithms. So starting from PDL algorithms, we require some kind of step detection and speed estimation. Oh, okay. And we had this kind of, how do you say, state transformation, transition system. And we can calculate steps by using this. And also we use the speed calculation from them. Okay. And also we had the terminal posture estimation by using the gyro and also using the Kalman filter. Okay. Okay. And by using the terminal posture and PDL, we integrate them to the direction estimation. So from the vertical view, you can see the person walks like this, And distribution of the direction is like this. So we estimate the direction of the working for this way. Okay. And then we use the posture to convert the coordinate and then integrate with the maps. Okay, so initially from the convert the system coordinate conversion, and then using the particle filter to estimate location, like this. So just skip them. So this is the final result. You can see these black dot is the particles. These colorful circles are the related magnetic field, and red line shows the trace, and pink is the estimated location. So this is IB building from the first floor and to second floor. It's now getting up to the stairs. A little bit difficult, but getting to the second floor. And the particle going up, but some of them is still not climbing up. But anyway, finally, particle distributed. However, it finally found out the correct location because we also using the map. We're using the map matching, so we can get the result like this. Okay, so I just skip the evaluation. And finally, I just briefly show about the indoor maps. If you can localize in indoor, you also required, you need indoor maps. And for indoor maps, there are several standards called CityGML is one of them. It has a LOD, level of details. And for indoor maps, we have to use the LOD4, so you can see indoors like this. And there's another standard called IFC. IFC is a CAD standard for BIM, Building Information Model. And usually it's targeted for the construction management, but it can be converted to the indoor maps. Okay. And there's another standard called Indoor GML. Indoor GML is standards. So if only you have maps, it's not easy to navigate inside of the indoors because you require to which room or which door is connected to which area. Okay, so this shows such kind of the connection between the area. However, it's not enough for the different kind of navigation. So we are trying to extend this kind of indoor GML. Okay, in the final, this is final stage slide. Today I show you about the state of the art for the indoor localized technology. So there's a lot of localized technology still, Wi-Fi based, IMS, audio, light, and I didn't explain about iBeacon, but iBeacon is also RF based system, and PDL and hybrid. And usually some of them each medium have its pros and the cons. So positive things, negative things. Okay. So for my my opinion, hybrid system have a future. So we require to investigate more about the hybrid system to integrate the different kind of localization system with the PDL. Okay. Thank you. That's enough. Any questions?
In your demo video, using the localization using the Wi-Fi, so how many particles are you using?
It depends on the system, but from the iPad system, I think it just uses 300 or something like that.
It looks like not real-time localization.
Because the Wi-Fi signal is not stable, so we use several Wi-Fi signal to estimate its power. Okay, so it's not easy to follow the real-time location. It requires several seconds to settle.
So it is not just a problem of the number of particles.
Not the number of particles. Okay, so we we use the PDL, so maybe PDL can estimate the location in the real time. So integration is very important. Okay.
About using a magnetic field, isn't there any effect of electronic device?
Of course, there's an effect. If you have a big motor or elevator, it's a big steel. So close to the elevator, maybe we have a effect from them. And if you car running around or big steel boxes moving, so maybe there's an effect.
And then how to deal with those cases?
I'm not sure. But however, it's not so okay. So close to the elevator is not good. But and there's this kind of building, we do not move the big steel usually. So, and maybe we can collect the data using the crowdsourcing. So if somebody moves there, and then if there's an error, so we can get using such kind of data to improve the survey data. Okay.
So what is the best precision?
It depends on the place. So yeah.
Roughly speaking. Roughly. Or
Briefly, you mean?
roughly.
Roughly, okay. So this is the one of the. So yeah, just using PDL, it has a 3.4, and also for Wi-Fi signal. Okay, I didn't. For PDL and the hybrid method, I just skipped, but it depends on location, but 7.5 meter or something for this evaluation. Yeah.
Quite big.
Yeah, quite big. Yeah.
Because indoor, there's more area, but we need more.
Yes, but this is the total, how to say, error. So what do I mean? It's some places very bad, some places good. So average is like this. So it depends on location. So if maybe you see for the stairs, it's not easy to estimate. Yeah, such kind of places estimation is very bad. Some places good. So it depends on what kind of the localization medium are there. So you have a significant difference on the magnetic field or Wi-Fi signals, it's easy. But if you don't have, so it's not easy. Okay.
Akai sensei, you mentioned in magnetic field localization, just join our autonomous driving team this spring. Just comment. He joined our team and collaborate localization.
Yeah, maybe you can.
So just comment.
Yeah, thank you.